Welcome to another edition of our discussion on mathematical method. Today, we shall be looking at one important tool in mathematics for solving certain kind of initial value problem and boundary value problem. The advantage of this particular tool is that it solves initial value problem and boundary value problem directly without necessarily obtaining the general solution of the IVP or the BVP. This particular tool is what we refer to as the Laplace transform. Laplace transform. So what is then the Laplace transform? The Laplace transform of a particular function is an improper integral of the product of the function together with certain kernel, and that kernel is defined as exponential raised to power exponential of negative of a particular function, say function of t. Now let's look at how to put that one mathematically. Suppose we let f of t be a real valued function defined for all t greater than 0. The Laplace transform of f of t is denoted and defined by Laplace of f of t equals 0 to infinity, integral 0 from 0 to infinity, e raised to minus st f of t dt. Now from this integral, e raised to minus st is the kernel of the integral, while f of t is the function whose Laplace transform is to be determined. Now what now makes this integral to be a proper integral is the bound from 0 to infinity, and it is an improper integral of second kind. Then how do you obtain the Laplace transform of a given function? From this integral and from the basic knowledge of our real analysis, we can write Laplace of f of t as limit is 0 as m approaches infinity, is 0 to m of e raised to power minus st f of t dt. If this particular limit, if what we have here converge, if everything here converges, then whatever it converges to becomes the Laplace transform of that particular function. However, as far as this course is concerned, as far as what we'll be doing is concerned, I may not necessarily look at it from the limit point of view. So I will just integrate directly, substitute the value of 0. Anytime I use infinity, what I mean is that I am taking the limit as the function is approaching infinity. Now, having said this, what are those things that we need to know as far as Laplace transform is concerned? Number one, we can show that Laplace transform is a linear operator. First stop. Laplace transform is a linear operator. How do we show that Laplace transform is a linear operator? How do we show this? It's very simple and straightforward. So to show this, let me call this one theorem or proposition. Proposition. Laplace transform is a linear operator. Then proof. We want to show that number one, the Laplace transform of constant multiplied by that function of t is k Laplace of f of t, where k is a constant. B, we also need to establish that the Laplace of function f of t and another function g of t, the addition of the two of them, is the same thing as the Laplace of f of t plus the Laplace of g of t. It should be noted also that these two properties can be combined together. The two I just want to show can be combined together. Say, instead of separating them, I can as well write them as a Laplace of k1 f of t plus k2 g of t is the same thing as k1 Laplace of f of t plus k2 Laplace of g of t. So, however, I will only show one of them. Let me pick the first one that we put on the board. So, let's take the first one. A. What is Laplace of k f of t? By definition of Laplace, I can write this one as a 0 to integral. It's integral from 0 to infinity e raised to minus st k f of t, because the given function now is k f of t. And from this, since k is a constant, it can actually move out of the integral sign. We now write k integral is 0 to infinity e raised to minus st f of t dt. By definition, what we have here defines Laplace, and therefore the answer becomes k Laplace of f of t. And that is the proof to the first one. The second one. The Laplace transform of this sum of f of t and g of t is defined as integral from 0 to infinity e raised to minus st into f of t plus g of t dt. We can open that bracket and have a 0 to infinity e raised to minus st f of t plus e raised to minus st g of t, everything now dt. So the two of them can be separated. We write it in this form: is 0 to infinity for that integral exponential minus st f of t dt plus integral from 0 to infinity exponential minus st g of t dt. And by the first principle definition of Laplace, the whole of this one becomes Laplace of f of t plus Laplace of g of t. And with these proofs for a and b, we have established that Laplace is indeed a linear operator. Laplace is indeed a linear operator. Now, so what we are going to do next now is to look at Laplace of some standard functions. So Laplace of a constant, how do we take it? If it is exponential itself, how do we take it? If it is hyperbolic function, particularly sin at, cosine at, how do we look at the Laplace transform? The Laplace transform of trigonometric function, how do we look at them? That will be the next discussion. And let's look at individual of this function that we just mentioned. Laplace transform of some standard functions. So let's start with the first one. If f of t is k is a constant, how do we take the Laplace transform of a constant? So by definition, Laplace of f of t is 0 to infinity, integral from 0 to infinity, e raised by minus st f of t dt. That's the definition. Now we now have Laplace of k, which is a constant, and that becomes integral from 0 to infinity, e raised by minus st k dt. Let us now integrate this. Integration by substitution, we are going to have minus k exponential minus st divided by s between 0 to infinity. Now, let us substitute the value. As t approaches infinity, e exponential minus st will be approaching 0, because the exponential is an Euler constant, and that is 2.718 on approximation. The denominator of that particular function will get, as t is getting arbitrarily large, will also be getting arbitrarily large. That, and the numerator is just constant 1. That is, what I mean is exponential minus st from the law of indices is 1 divided by exponential st. So as the t is getting arbitrarily large, this particular function is also getting larger and larger. And from what you have learned in elementary school, the higher the denominator of a fraction, the lower the fraction becomes. And this one will be moving towards 0. So therefore, with respect to the limit of this, the whole of this expression is going to become 0 with taking the limit as t approaches infinity. So that the Laplace of k becomes 0 minus, now substitute 0 for t. Exponential 0 is 1, and we are left with minus k divided by s, which eventually becomes k over s. So therefore, the Laplace of k equals k divided by s. So please note this formula. Example, just simple example. What is the Laplace transform of say 8? The Laplace transform of 8 is simply 8 divided by s. What is the Laplace transform of pi? Pi there is a constant, and that means that I'm going to have pi divided by s. And that is the Laplace transform of a constant. Let us take Laplace transform of another function. Suppose our f of t is exponential at. How will the Laplace transform looks like? 2. If f of t equals exponential at, the Laplace transform of exponential at by definition is 0 to infinity exponential minus st multiplied by exponential at dt. Now, for this problem, we must ensure that we retain this negative as far as integrating this function. We must retain this negative, so that at the end of the day, by the time we substitute and we take the limit as t approaches infinity, it will decay. It will not be growing. So, and how do I mean? Apply the rule of indices to this function. We have e raised to power minus s minus a into t dt. Let us now integrate. The integral of this gives exponential minus s minus at divided by s minus a between 0 and infinity. So with respect to infinity, we take the limit, and from what I explained in the previous example, under the Laplace of a constant, then with respect to infinity, the whole of this expression becomes 0, and that means that I have 0 minus, substitute 0 for t here, the whole of this expression becomes 1. Then we are going to have that result as minus 1 divided by s minus a, so that the Laplace transform of exponential at becomes 1 divided by s minus a. Take note of this formula. As an example, the Laplace transform of e raised to power 3t is 1 divided by s minus 3. And the Laplace transform of, say, e raised to power minus 10t will give us 1 divided by s minus 10. Because that's what I have here, minus 10. And the final result becomes 1 divided by s plus 10. So that is the Laplace transform of exponential at. So number 3. What if it is a parabolic shine at? How will it look like? That one of a sine at and the cos at, they are just extension of the exponential, because the definition of sine at and cos at has relation with exponential. The Laplace transform of sine at equals integral is 0 to infinity exponential st then sine at dt. By definition, is 0 to infinity e raised to power minus st. The definition of sine, it is exponential at minus exponential minus at divided by 2. That is the definition of sine at. So with this definition, I can expand the bracket by saying half integral from 0 to infinity e raised to power exponential raised to power minus s minus a into t minus exponential minus s plus a into t. What have I done? What have I done here? What I have done here is very simple. I expanded the bracket and I applied the law of indices simultaneously. The expansion of this is exponential minus st exponential at. The law of indices holds, and do not forget, we need to retain the negative of our kernel. So now, retaining this negative makes the first expression to become this, and make the second expression to become that. So the integral, so let us integrate the two functions separately. The integral of the first one will give us minus exponential minus s minus at divided by s minus a. While the second one, I have minus, and the integration will also give us another negative. So there will be two negatives, which turns this positive. Exponential minus s plus a t divided by s plus a between 0 and infinity. With respect to infinity, everything I have inside the bracket becomes 0. Minus the next bracket, with respect to 0, the whole of this one becomes 1. That is minus 1 x minus a and plus 1 divided by s plus a. So that I have 1 divided by 2 into bracket 1 divided by s minus a minus 1 divided by s plus a, because the negative needs to open up the inner bracket. So let us take the LCM. Of course, 1 divided by 2 into my LCM is s squared minus a squared. S squared minus a squared divided by x minus a will give us s plus a. Multiplied by 1, I have x plus a minus x squared minus a squared divided by x plus a will give us s minus a. Multiplied by 1, we have s minus a. With respect to what I have, if I open the bracket, s cancels out, then I have 2a at the numerator. So the 2 cancel out the 2 outside, then the final result becomes a divided by s squared minus a squared. And that is the Laplace of sine 80. Example. Give an example on this. Example. What is the Laplace of sine 70? Of course, the answer will give us now observe that at numerator, the coefficient of the argument makes our numerator, while our parameter at the kernel, the square of that parameter minus the square of the coefficient of our argument makes up the denominator, difference between the difference between their squares, so that this becomes 7 divided by s squared minus 7 squared, which gives 7 divided by s squared minus 49. Let's take another one. If f of t is cos 80, how do we get the Laplace transform of that function? Like I said, while we're looking at sine 80, cos 80 is also an extension of exponential function, because cos 80 by definition is exponential 80 plus exponential minus 80 divided by 2. So we should not have problem handling this, since we have done that one of sine 80. So by definition, the Laplace of cos 80 gives 0, integral 0 to infinity exponential minus st into bracket exponential 80 plus exponential minus 80 divided by 2. We have this, then the t. So let us open the bracket. Is 0 to infinity on the integral, 1 divided by 2 outside, exponential minus s minus 80 plus exponential minus s plus 80 everything dt. The law of indices has been used in the opening of the brackets. Now let us now integrate. The integral of the first term there gives minus exponential minus s minus 80 divided by s minus a minus exponential minus s plus 80 divided by s plus a between 0 and infinity. With respect to infinity on the limit, the whole of the bracket becomes 0 minus substitute 0 for t. I have minus 1 divided by s minus a, and I have minus 1 divided by s plus a. So the negative here opens up the bracket to half into 1 divided by s minus a plus 1 divided by s plus a. We take the similar step with what we did under the shine 80, and that gives the LCM to be x squared minus a squared, and the first time here is x plus a plus s minus a. A cancels out, then we are left with s plus s, which is 2s, and the 2 cancel out this. The final result is s divided by s squared minus a squared, where s is the parameter of our kernel. As an example, let us take the Laplace transform of say cosh, say 3 divided by 2t, and that gives the parameter at numerator s divided by s squared minus 3 divided by 2 all squared. So simplification gives 4s divided by 4s squared minus 9. That solves the problem. Upon simplification, that's what we are going to have. Let's take 3 more functions. And the next function I want to consider is number 5. If f of t equals sine 80, that is trigonometric function. So how do we approach this? There are 2 ways of approaching this. However, I will only consider one as far as this class is concerned. So Laplace of sine 80 gives, by definition, integral from 0 to infinity exponential st sine 80 dt. What do we do? We are going to integrate this one using the method of parts. This is integration by part because it combines exponential and trigonometry. From our elementary calculus, we know how to do this. So integrating this one by part will give us, we write exponential st. What I have here is s. Multiplied by what you have here, you have s sine 80. The center sign will always be negative. Differentiate this. Sorry, I have minus. I have this to be cos A cos 80, all divided by minus s all squared plus a squared. I have integrated by part from 0 to infinity. So from here, what do we have? Now, with respect to the infinity, if we take the limit here, this particular spot is going to decay, and it's going to decay to 0. So the whole of this expression becomes 0 with respect to infinity. With respect to 0, sine 0 is 0. So this particular terms goes out, while this one becomes 1, and cos 0 is also 1. So we are only left with minus a divided by what we have at denominator. And what I'm trying to say is that the upper bound there, upon taking the limit as t approaches infinity, will give us 0 minus, with respect to 0, the whole of this expression here becomes 0. This becomes minus a divided by s squared plus a squared. So that the Laplace of sine 80 becomes a divided by s squared plus a squared. Take note of that formula. So, as example, the Laplace transform of say sine say 11t, that gives the coefficient of the sine of the argument of sine there, which is 11 divided by s squared plus 11 squared, which is 11 divided by s squared plus 121. So that is the Laplace transform of sine. And we have taken an example here, sine 11t. The next function we are going to consider is cos. Laplace number 6. If f of t equals cos 80, then what do we have? By definition, Laplace of cos 80 equals integral from 0 to infinity exponential st cos 80 dt. Integrating by parts, we have exponential minus st into minus s cos 80 plus a sine 80 all divided by minus s squared plus a squared between 0 and infinity. With respect to infinity, upon taking the limit as t approaches 0, we have 0 minus bracket. With respect to 0, the whole of this one becomes 1, this becomes 0 because sine 0 is 0, and what I have here is cos 0, which is 1. 1 multiplied by minus s will give us minus s divided by s squared plus a squared. Let us now open the bracket. By opening the bracket, the Laplace of cos 80 becomes the Laplace of cos 80 becomes s divided by s squared plus a squared. That is the Laplace of cos 80. And finally, no, before we take the final one, let us take example. Suppose we have Laplace of cos, say 90. What will the final answer be? The final answer is s divided by s squared plus 9 squared, and that gives s divided by s squared plus 81. Let's now take that of polynomial of degree n. How do we take the Laplace of that? And that will be the final function we are going to consider as far as this particular class for today is concerned. Laplace number 7. If f of t equals t raised to power n, the Laplace of t raised to power n is 0 to infinity on integration exponential minus st t raised to power n dt. Now we're going to integrate this one using method of part. We integrate by part. Here our u is the exponential, is the polynomial t raised to power n, and our dv is e raised to power minus st. Why? because t raised to power n is easily differentiable, while e raised to power minus st is a function that is easily integrable. So du, call this one equation 1. Du gives n t raised to power n minus 1 dt, while our v gives minus e raised to power minus st divided by s. Now apply the rule that the Laplace transform of t raised to power n now will be uv minus integral v du, which gives uv minus t raised to power n exponential minus st divided by s between 0 and infinity minus integral 0 to infinity. The v, our v is negative, so this turns this particular one positive. Then I have nt n minus 1 exponential minus st dt. Now, let us now discuss these results. With respect to infinity, upon taking the limit, the exponential minus st is going to decay, and that will give us a 0. With respect to 0, the t raised to power n is also 0. That means that the first term here turns out to be 0. We are left with the second integral. So that the Laplace transform of t raised to power n gives n, this divided by s. N divided by s integral from 0 to infinity t raised to power n minus 1 exponential minus st dt. Now let us observe very well that what we have there defines what we have in equation 1. And how do I mean? I mean that Laplace transform of t raised to power n gives n divided by s Laplace transform of t raised to power n minus 1. That's what we have. So here we now deduce that if n is 1, n equals to 1, I have Laplace of t to become n divided by s Laplace of 1. And we know that Laplace of 1 is 1 divided by s. So that this becomes n divided by s, 1 divided by s. And that gives us n divided by s squared, which is the Laplace of t. When n equals to 2, we have Laplace of t squared. And Laplace of t squared, let's call this one equation 2. Substitute it into equation 2. We have 2 divided by s Laplace of t. There's a value for Laplace of t. Sorry, there's a mistake. I'm supposed to substitute 1 here. Sorry. That it's supposed to be 1 and this is supposed to be 1, not n. There's value for n. So which will give us 1 times 2 divided by s raised to power 3, which can now be written as 2 factorial divided by s cube. Let's take 2 more values for our n and see whether there is going to be any relationship, if at all it exists. Suppose n equals 3. That means the Laplace of t raised to power 3 equals 3 divided by s Laplace of t squared. And there's a value already for Laplace of t squared. That gives us 3 divided by s, 2 factorial divided by s cube. 3 times 2 factorial will give us 3 factorial divided by s raised to power 4. Let's take one more, then we generalize. N equals to 4. Laplace of t raised to power 4 equals 4 divided by s Laplace of t raised to power 3, which give us 4 divided by s Laplace of t raised to power 3 is known to be 3 factorial divided by s raised to power 4. So 4 multiplied by 3 factorial gives 4 factorial. Gives Laplace of t raised to power 4 gives 4 factorial divided by s raised to power 5. Now, let me pause here. Do we observe anything? Let me write the previous result. We have Laplace of t to be 1 divided by s squared. We have Laplace of t squared to be 2 divided by s cube. Laplace of t cube to be 3 factorial divided by x raised to power 4, and Laplace of t raised to power 4 gives 4 factorial divided by s raised to power 5. Now, if we observe, denominator has relation with the power of t. When the power was 1, this is 1. When the power was 2, we have 2 factorial. We obtain 3 factorial when the power of the polynomial was 3, and we obtain 4 factorial when the power was 4. So therefore, the Laplace of t raised to power n will have given us n factorial n, looking at that relation. Also, let us look at denominator. When t was power of 1 here, the s was power of 2, 2 we have 3, 3 we have power of 4 here, 4 we have power of 5 here. Now that tells us that the relationship between the power of s and power of t is just the difference of 1. That is, if we add 1 to the power of t, we are going to obtain the power of s. Add 1 to 2, you have 3, add 1 to 3, you have 4, add 1 to 4, we have 5. Now that we have it as n, then we have Sn plus 1. It should be noted that we can as well prove the Laplace of t raised to power n using what we refer to as gamma function. However, because gamma function is not the major focus of this class, the reason we pass through this approach. So when we get to gamma function, we will look at how we can use gamma function to actually obtain the Laplace transform of t raised to power n. Or perhaps we put the relationship that exists between Laplace transform and gamma function. Example, Laplace transform of t raised to power 8 is 8 factorial divided by s raised to power 9. That's the problem. As far as this question, this class is concerned also, I will try as much as possible to avoid a rational power of t, because we do not have the knowledge of gamma function presently. The moment we have the knowledge of gamma function, then we can take the Laplace transform of t raised to power a rational function, because at that time we will have seen the relationship between the Laplace transform and gamma function. So far in today's class, we have been looking at one important tool in mathematics to solving initial value problem and boundary value problem, and that is the Laplace transform. We define what Laplace transform is. We emphasize the fact that the definition of Laplace transform make it an improper integral of second kind. We also establish the fact that the Laplace transform is a linear operator. Also, we obtain the Laplace transform of some function. We started with constant, we look at exponential, we look at hyperbolic, specifically we look at 2 of them, sin AT and cos AT. The next one is the trigonometric function. We look at sin AT and cos AT. And finally, we look at polynomial. we may want to ask, why is it that for both hyperbolic and trigonometric function, we didn't look at the remaining 4 functions? That is, for instance, for trigonometry, we didn't look at tangent, we didn't look at secant, we didn't look at cosecant, we didn't look at cotangent. Although that is above this class, but we should know that the aforementioned function are not what does not satisfy some criteria that will make them that make us to calculate, to find their Laplace transform. They do not satisfy some criteria that will make us to calculate their Laplace transform, and those criteria, or that particular criteria, is above this particular class as far as the scheme we are using is concerned. I am Ridwanullah Inyoda Abdulgani. Till next time we are going to meet, I wish you best of luck. Thank you and kind regards.